Welcome to Numerical Methods for Scientists and Engineers with Pseudocodes. Video 3. Inverse Power Method. The inverse power method is an iterative algorithm to find simultaneously the smallest eigenvalue in magnitude and its associated eigenvector of a matrix. Since the eigenvalues of the inverse matrix are the reciprocals of the eigenvalues of the original matrix, applying the power method to the inverse matrix would converge to the dominant eigenvalue of the inverse, i.e., the smallest eigenvalue of the original matrix. But inverting a matrix is computationally expensive, especially for large matrices. So instead of explicitly computing the inverse, we solve a linear system at each iteration. The inverse power method is designed to determine the smallest eigenvalue of a matrix and its associated eigenvector. To achieve this, we rearrange the standard eigenvalue problem as follows. Where mu equals 1 over lambda and A is a non-singular matrix. The power method can be applied to find the dominant eigenvalue, mu, corresponding to the smallest value of lambda. In practice, the computation of the inverse matrix is avoided by noting that the power iteration is equivalent to solving the linear system of equations gives the eigenvector estimates. A judicious strategy to solve the linear system is to employ LU decomposition of A. Once we obtain the L and U matrices, we can start the iteration process with an initial guess such that the infinity norm of the initial guess is non-zero. The system is solved by a forward elimination, followed by a back substitution. A new estimate for the smallest eigenvalue, in absolute value sense, is computed from where prior steps for the current step are calculated by normalization. If mu is less than 0 at any current iteration step, the eigenvector is updated as follows. The iteration procedure is continued until the stopping criterion is met. The advantages of the inverse power method are: the inverse power method is easy to implement, targets the smallest eigenvalue directly. It can provide very fast convergence in cases of symmetric matrices. It avoids explicit matrix inversion. It requires low storage. It is also suitable to find complex eigenvectors. The disadvantages of the inverse power method are: it requires the matrix to be invertible. Only one eigenpair can be determined. The rate of convergence may be slow if the eigenvalue is not well separated from others, e.g., clustered eigenvalues. The convergence speed depends on the initial guess. Let us consider the following matrix. We would like to determine the smallest eigenvalue in magnitude using the inverse power method. We will use 0.5 times 10 to the minus 6 as the stopping criterion and a vector of 1s as an initial vector to start the power iteration. The inverse power iterations require the solution of the following system of linear equations presented in matrix equation form. Since the matrix A remains unaltered throughout the iteration process, we can minimize the computation time by decomposing A as LU. The Doolittle decomposition yields the following. And then we can solve the lower and upper triangular systems of equations at every pth iteration. We begin with the initial guess vector and solve the lower triangular system, Lz equals x0 using the forward substitution algorithm, which gives. Then, we solve upper triangular u x1 equals z using the back substitution algorithm, which yields. The inner product of eigenvector estimates x0 and x1 yields 1.046 repeating 21, while the inner product of x0 by itself gives 4, from which mu and lambda can be calculated as follows. The current eigenvector estimate is normalized with the infinity norm before the next iteration step. We begin the second step with the current eigenvector estimate x1 and solve the lower triangular system Lz equals x1 using the forward substitution algorithm, which gives. Then we solve upper triangular u x2 equals z using the back substitution algorithm, which yields. The inner product of eigenvector estimates x1 and x2 yields 0.952946. The inner product of x1 by itself gives 2.875713, which leads to mu2 values of 0.331377. The current estimate of the smallest eigenvalue, lambda 2, is found as 3.01771. The eigenvector estimate for the next iteration is normalized before the third iteration step. We repeat this process for the third, fourth, and subsequent steps. The results of the iteration progress is tabulated as illustrated. Note that the smallest eigenvalue estimates improve significantly at each step. This iterative process continues until the difference between the eigenvalue estimates and the norm of the displacement vector is less than epsilon. The iteration process results in 6 decimal place accurate estimates in 7 iterations. The smallest eigenvalue is found to be 3, and the associated eigenvector is 0, 1, 1, 1. With this note, we end this video lecture. That is all for now. See you next time with another topic. Bye.